How you doing? I'm Mr. Rose, and today we're going to continue talking about oscillations with damped oscillations. Now, a damped oscillation is something slightly different than simple harmonic motion. Here I have a picture of a pendulum that I started here, and it started swinging back and forth. So starting here, ending here, and in real life we know that's not going to swing back and forth forever and ever. In fact, we know that eventually it's going to slow down and stop, which is what I tried to depict here, where I started in a negative amplitude just because that's the way I drew my picture, and it slowly, you can see, has this sine motion that we're used to that comes down and eventually comes to zero. Well, I also drew a spring here because in real life, if I take that spring and I let it go, that spring is going to oscillate up and down until it eventually slows down to stop. Now, what is interesting is very similar to air resistance, if you remember when we spoke about that the damping motion or the damping force is not actually relevant to its amplitude. It's actually relevant to how fast it's going, its velocity v. Now, when we did air resistance, we talked about it and it was given to us that air resistance or the air friction force, because it is a force, was given by that negative constant b. Our force or damping force is just given by the equation, very simple, negative b times v. Now, you also might remember that there are things, if it is going faster and faster, it could be possibly negative bv squared. There are even some things that model negative bv cubed, but for our most part, our general equation is going to be a damping force of negative b times v. Now, there are three types of damping we're going to talk about. Now, you may see that I have a car here, and I want you to think about a car, your experience driving in a car, or driving a car as you've experienced through life. First is our underdamped motion. Now, underdamped means I'm going to take my object of the car, it's going to hit something, it's going to bounce back and forth and back and forth and back and forth. So as you can see, my graph goes, and I have these purple lines. Now, those purple lines should be relatively exponential. They may not be the best exponential here, but this purple, the graph rather itself, resides in this envelope, we call it. And that envelope, you can see, gets smaller with time. And as I said, it's an exponential. We know that things that get smaller as a function of time come out to be this exponential function. So what is that exponential function? Well, we know our amplitude A is getting smaller and smaller and smaller. So my amplitude of A with respect to t is what I'm calling A naught, whatever my initial position was, times e to some n times t. Now, n is something very specific here. N for us is negative b over 2m, where that negative b comes from my damping force, that b, that damping constant, depending on the fluid that we're going through. So we can see here, if b gets very, very big, it's going to get negative faster or slow down very, very quickly. So when I sub in my b squared over 2m into my equation, I have the amplitude for an underdamped oscillator at any time of e to the negative b over 2m times t. The next, if we have underdamped, I have something that is overdamped. Now, overdamped is something you can typically think of too much friction. How's there a thing? There's too much friction. Well, essentially, an overdamped oscillation is something like a pendulum that never actually makes an oscillation. So you can think of a pendulum trying to swing through concrete. It's not going to oscillate. Eventually, you can see it's a very, very long exponential that goes all the way down to t. There is no oscillation. Way too much friction. Then we have, kind of like the three bears, we have too little, we have too much, just right, the critically damped solution. You can see here, critically damped solution also comes to rest fairly quickly. All of its energy is going to leave the system. Damping is because we have energy going back into the system, air resistance, heat, friction, some kind of force. All of our energy returns back into the system here in the ample amount of time. It happens before any oscillation, very similar to overdamped. The difference is all of the energy gets back to the system as fast as possible in this critically damped solution. This is as long as possible. This kind of keeps going for way too long of a time. And like I said, if you think about a car, This is if you had a pothole and your shocks are just shot, your shock absorbers. You bounce and you bounce and you bounce up and down way too much. An overdamped solution is like if your shocks are shot and they're just too stiff. So you almost like a skateboard. You bang, you hit a pothole, you feel everything. The critically damped solution is a perfect car. A brand new car, drive it off the lot, you hit that bump, you don't even feel it because it releases all of that energy right back into the system as fast as it possibly can. Before we keep going with this example, I want to take a moment because this is what we're going to talk about. We're going to talk about a damped solution with a spring oscillating back and forth. We want to compare that to simple harmonic motion. So here I have a spring, mass hanging on a spring with spring constant K at 3 different times, time 1, time 2, and time 3. Here I set it up with no gravity. I can do that here on the board. And then all of a sudden I turn gravity on and this mass hangs down that spring. Well, eventually it's going to come down to rest, and I want it at rest. We can see that it fell down from my initial position some distance s. Now, it's not spring. Here it's an equilibrium, and I have a simple free body diagram. The force of gravity, mg, is coming down. My spring force, ks, or k times the distance, is moving up, and it's just sitting at rest. Now, finally, I take it, and I want to oscillate that back and forth, and it is a perfect system, so it is going to undergo simple harmonic motion. Undergoing simple harmonic motion, I'm now at some distance x. It's still not at that equilibrium position, so I have s minus x here, I have some distance x, and it's going to be oscillating back and forth. I apply Newton's second law, everything comes back to Newton's second law. F equals ma, where my force is the spring force, plus the force through gravity equals my mass times acceleration. My spring force is that distance s, minus x, where that is right now, right? It's just k times x minus mg equals ma. And I can see after I distribute that ks through that this is just my force through gravity, my mg. Now, something you may not have realized as this is oscillating back and forth, even with that external force of gravity. We have mg minus mg. Those guys are going to cancel each other out. I'm just left with negative kx equals m d squared x over dt, or ma. This is my equation for simple harmonic motion. It comes out no matter what we do, just like we did with a pendulum, just like we did with that oscillation going back and forth on a frictionless surface. Well, now let's add a little bit of real life to this. Here I drew another curve. Let me get on this side. Here I drew another damping curve. Now, it looks very much like my underdamped solution here, but just so we can see it, not necessarily an underdamped solution. I know that my damping force is negative b times v, and I'm going to apply F equals ma, where I have my spring force, negative kx. Now I need my damping force, negative bv equals ma. Now, just to make life easy, I'm going to make everything positive, bring these guys to that side, and set everything equal to 0. So now I have ma plus kx plus bv equals 0. All of my forces summing up to be 0, which is a great application of Newton's second law. Now I'm going to make it look like a little bit of calculus. Change my acceleration into m d squared x over dt squared. Keep my damping force, kx, plus my b times v, I'm sorry, that's the spring force, I apologize. My damping force is my b times my velocity, all that equals 0. Now this is my equation of motion for damped harmonic motion. I'm sorry, for a damped oscillator. It's not harmonic motion, it's not repetitive. It's very similar, negative kx equals m d squared x over dt. I can bring that over, say that's equal to 0, but I have this extra term, this term of velocity, because we know that my damping force is related to the velocity. So what is the solution for this? Again, a second order differential equation, we need to guess the solution. Well, earlier we learned that my equation of motion for a simple harmonic oscillation was x of t at position is my amplitude a cosine omega t. Well, this is going to be very similar, except now I need to put in my new amplitude. I know amplitude is no longer a constant, but is a function of what we just learned. It's a function of my original amplitude, a naught e, negative b over 2m times t. I put that right into my equation. So my new equation of motion, or position rather, is ae negative b over 2m times t. times the cosine of omega t, except now I have a new omega term. I'm going to present this to you without proof that omega prime is actually the square root of k over m minus b squared over 4m. Now this is a really important term. Again, it's provided without proof because it comes out of our second order differential equation. But if I look at this, I can still relate things that we know from our class. We know that angular frequency is related to a frequency just by 2 pi times omega. So I can say my frequency prime, so to speak, is 2 pi times k over m minus b squared over 4m squared. This tells us a lot of things. From this small interpretation, I think I'm off the screen here, but my screen went dark, so let me stay over here. From this small interpretation, I can examine just what's under my radical, and we can figure out what kind of oscillation we have. So if I look at this, first of all, I know that that needs to be a positive value. I can't have negatives underneath my square root. Secondly, if I say that k over m is equal to b squared over 4m squared, or rearranging that, if I'm setting them equal, I can say b squared is equal to 4km. What does that tell me? Well, if those two are equal, then my frequency is 0. If my frequency is 0, that tells me there's no oscillation. What does no oscillation tell me? No oscillation tells me one of these two things. And I'll tell you that no oscillation where frequency equal to 0, and you're going to see it in a minute, means that it's a critically damped solution. And that's what I want. That's why I have my little happy face there. I'm getting all of my energy back into my system as fast as possible. Well, let's look at our other two possibilities. If b squared is much, much bigger than 4km, well, if b squared is very, very big, I'm going to have a frequency that is huge. If I have a frequency that's huge, that means it's going to take a long, 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 long time to oscillate, or in fact, no oscillation. An over-damped solution, way too long to get that energy back into the system. Likewise, if b squared is less than 4 times k times m, I'm going to have something that oscillates for a long period of time. An underdamped solution, or showing some oscillation, which was kind of the picture that I drew here, just for argument's sake. Now, one last thing, again, if I look at all of this, specifically my damped solution, if b is equal to 0, that means I have no damping force. If b is equal to 0, e to the 0 is 1, and now I have just a times t. That's what we had before. Cosine omega prime t, if b is equal to 0, I'm just left with, instead of omega prime, omega, and I'm back to my simple harmonic motion. So we can see that there is a strong relationship between these two, but in real life, you're either damped if you do, damped if you don't. Thanks for watching. Remember to like, comment, share. I messed that up again. Feel free to leave comments or questions, and that's all I have for you today. Thanks for watching.